Filters are voltage dividers that use reactive components. So what do I mean by that? It's a good universal statement for filters, but let's try making a voltage divider with a reactive component and we'll see what that statement means. Um, for our reactive component, we could use a capacitor, we could use an inductor. Um, we'll stick with a capacitor, and for this video, we'll just do maybe one or two of the simplest types of filters we can make sort of to get this whole concept started. So here we have a voltage divider that uses a reactive component, C1. Instead of two resistors, R1 and R2, we're going to use a resistor and a capacitor. And that's what's going to give us a filter. The whole purpose of a filter is to create an output that does not treat all frequencies the same. You could have a filter where low frequencies have a higher output, and that would be a low pass. And then when you get the frequency too high, the output starts to fall off. You can make a high pass filter. For that type of filter, high frequencies would have an easy time. You'd have a high output, and the low frequencies would not get through to the output. You can do other types, band pass, band stop, where there's a middle range of frequencies that would have a low output. So here's your output taken as we normally do for a voltage divider. This, of course, is a very simple type. This resistor capacitor pair would be known as a pole. And so this being the simplest type of filter, this would be known as a single pole filter. That's all we have, is just one pair of a resistor and a capacitor that are giving us the voltage divider that will create our output that will vary depending on frequencies. So your frequency would be really, we'll take a sine wave here, and we would put our frequency source across the voltage divider, and then our output would vary depending on frequency. That's the gist of a filter. It'll have a varying output that's dependent on the frequency. So like we said, a low pass filter you'll have a high output for low frequencies, and then the frequency will decrease. The output will decrease as frequency increases. That would be a low pass filter. And a high pass filter, just the opposite. So let's examine our simple single pole filter, which is a voltage divider that's using a resistor and a capacitor. Our input voltage is here. Our output voltage is here. So I think you can notice the output voltage is the voltage across C1 for our example, for this filter. So V out is also the voltage across the capacitor. So let's look at that. What is the voltage going to be across the capacitor? If you remember all the way back to the DC course, basics of voltage division, if it was two resistors, of course, the voltage divides up according to the resistance in the circuit. Then when we moved on to the AC course, we had to adjust our thinking to a more universal thought that its impedance is really the way to go with AC involved and in reactive components. So basically, this voltage here at the input is going to divide up with this voltage divider according to impedance. So how much voltage will fall across the capacitor depends on the impedance of the capacitor compared to the total impedance of the circuit, the voltage divider. So it'll be a certain amount of Vn dependent on C1's impedance compared to the total impedance. And then you have to remember the trick here, the thing that makes it a filter is this impedance varies with frequency. Also, if you remember from the AC course, the impedance of a capacitor is very close to the same thing as the reactance, provided the equivalent series resistance of the cap is low. So that's a fair estimate to make. So that would be the reactance of C1. And then the impedance of the voltage divider, the circuit as a whole, is of course the Pythagorean theorem here, where we have to geometrically add reactance and resistance. So there's that to get the total impedance. And one step farther, the reactance of the cap, of course, is 1 over 2 pi fc. So all of this would be the calculations that are needed to get specific numbers. But let's move all the way back to just understand the basic operation in a broad sense. We've got a resistor and a capacitor. Let's take very low frequency, even all the way down to 0 hertz, and see what the voltage division looks like. So our output, we're going to look at as it occurs over a range of frequencies. So we'll start low, and then as the frequency increases, let's try to understand what happens with the voltage division. So at 0 hertz, or very low frequencies, the impedance of the capacitor is going to be very high. If you remember, at 0 hertz, it looks like the open that it is. It's just 2 plates separated by an insulator, so a dielectric. So C1 is going to be very high impedance, in fact, infinite impedance at 0 hertz. It will get all of the incoming voltage. All of Vn will fall across C1. It'll claim all the voltage because its impedance is infinitely high, theoretically, but at least very high in reality. So it'll get all the voltage. So that means our output will be here with the full voltage, and we can start there. And then think about what will happen as frequency goes up. As frequency increases, what happens to the impedance of a capacitor? It goes down. As C1's impedance decreases, it will get less voltage across it as it competes for voltage with R1. Remember, the voltage will divide up according to impedance. So C1's going to lose impedance. R1, do you remember how R1's impedance changes with frequency? It does not. So resistors are not reactive. R1 will have the same impedance. If it's a 10K resistor, it'll be 10K for every frequency. So 10K, if we put that as an example, we could write that here so we remember that's what we talked about. That is going to be not changing with frequency. But C1's impedance will be changing. It'll be decreasing. So as C1's impedance decreases, it will get less and less voltage. Remember, C1's voltage is the output voltage. So it just means the voltage is going to decrease. The output's going to decrease as frequency increases. That's a low-pass filter. Low frequencies pass through, and then higher frequencies have a tougher time. So for this example, we have a single pole low-pass filter. When the output drops to 0.707 of what it was here, so whatever this was, that would be known as the pass band. When it drops down to 70.7% of what it was, that's what we identify as the cutoff frequency. 0.707 is also the half power point. It's also the point that is 3 decibels down from where it was up here. So I started this video by drawing the filter in a way that helps you visualize the voltage divider action, sort of in a familiar way, I hope, from when we introduced voltage dividers. So that's why I drew the filter sort of like this circuit. That's not how you would draw a filter circuit conventionally. That's over here. I'm showing it. So you would not draw them like this, but it makes sense, I think, to draw them like this. And if you can see, that is the same circuit. So maybe take a minute. V in is the same, right? And then, you know, because V in, it falls across R1 and C1. And the output is taken across the cap, and that's still the case. But you can probably see that they are the same circuit. This is a better way to draw it because it shows that you're going to have an incoming signal with some filtering action and then an output signal. So your signal comes in and your signal comes out of the filter here. So we had used a 10K resistor, maybe we mentioned. Let's put a value for C1, 0.01 microfarads. So let's put that here, 0.01. And I want to show you just how easy it is to calculate the cutoff frequency for your filter. So we would have a single pole, low pass filter, and the final question would be, what's the cutoff frequency? We know that the cutoff frequency is going to be when the frequency that causes the output to be 0.707 of what it was. So when this equals 0.707, that's when your cutoff, that will point out your cutoff frequency. You could do the algebra on this and derive the cutoff frequency formula, but no need. It's a very simple formula. It's easy to, I think, have in your head. Easy one to memorize. So let's show you what that is. But just so you know, it's, once again, it's not magic. It comes from solving here. If you look at when the ratio of C1's impedance to the total impedance is 0.707, that's when it'll claim 0.707 of V in, and frequency is buried in here, right? It's buried here. It's buried here. It's also in here. So you'd have to do a little bit of algebra and solve for F. Well, if you do that, or you don't have to, but you could make your algebra teacher proud, I'm sure. You could solve for F, and what you would find is, I'll double check that I'm right about that. A nice formula that's nice and simple. So filters, they don't get too crazy. I mean, at least with the calculations. Not like in the AC course when we had to analyze an RLC circuit. I think that kept us busy. But cutoff frequency for a filter, just this. Try it. Do the math. Get your calculator out, and you'll have these values to plug in and solve. You should find your cutoff frequency for this single pole low pass filter is a 1.59 kilohertz. Running out of room here. There we go. That means right over here you'll have identified the frequency where the output will have dropped to 0.707 of what it was. I'd like to do just one more thing. For this video, I don't want to go too far. I want to just keep it an introduction to filters that doesn't run away with itself too and get too complex. Just let the dust settle on this. But the one more thing I'd like to show you is, let's see what happens if we exchange places here. So if we put the resistor here, right, and we put the capacitor here, and let's keep the values the same. Okay. We could do it back over here on our model that really shows us the voltage division very nicely. So let's do that real quick. So the capacitor would be up here now, and the resistor would be down here. V out is still across this area, but now it's across the resistor. The resistor's impedance does not change with frequency, but the capacitor's impedance does. And let's see what happens. At high frequencies, this impedance of the capacitor will be very low. In fact, it starts looking like a short, right, at very high frequencies. So what we have is, let's maybe go down here and say at high frequencies, our output, all of V in falls across the resistor because the capacitor's impedance is very low at high frequencies. Then as frequency starts to decrease, the capacitor's impedance will increase and it will claim some of the voltage, and in fact more and more of the voltage. As frequency goes lower, the impedance will go higher for the cap, and it will steal more of the voltage, and there'll be less voltage falling across the resistor. So the voltage will go down. So let's draw that as frequency decreases, the capacitor's impedance increases, and it claims more of the voltage as it sits in a voltage divider relationship, with R1. So frequency is going down, capacitor's impedance is going up. Yeah, this kind of a thing. Didn't draw that real well. I meant to sort of have more of a roll off there. Okay. What does that look like? Looks like a high pass. In other words, high frequencies pass through the filter, low frequencies are attenuated. It's still just one pole, so it's a single pole, but now we would have to call it a high pass filter. One cool thing, the formula doesn't change. To calculate the cutoff frequency for this filter, we kept our values of R and C the same, and in fact, the formula is the same for either arrangement. So for our high pass, it also has a cutoff frequency of 1.59 kilohertz, which is why I drew it to cut right through that same point. So whether we make a low pass or a high pass with our 0.01 microfarad and our 10K, we get the same cutoff frequency, of course differing results, whether it's a high pass or a low pass type of filter. It is interesting that the formula doesn't change. If you explore that mathematically, you will see that the reason it doesn't change is that the 0.707 point here occurs when these impedances are equal. So, boy, it might be hard to see that. So when that equals, oh my gosh, that's the key. You'll find that the 0.707 ratio here that you're looking for occurs when this impedance matches this impedance. So that's why you can exchange them, and this calculation doesn't change. Or another way to look at that is, you have maybe I can have room to do it. You have this capacitive impedance or reactance, right? Get this out of the way. And if you have the same amount of resistance. Remember, the impedance is essentially the same as the reactance for the cap, and the impedance is the same as the resistance for the resistor. So what we're saying is the impedances, if the impedances are the same, then the total impedance is right here, right? And you have a 45-degree angle. So now that 0.707 should start popping into mind maybe. But what we're talking about is the ratio of impedance to total circuit impedance, or impedance to total circuit impedance. It's the same whether you have a low pass, which would be this impedance, to the total circuit impedance is how much voltage you get. Well, the length of this side, that ratio to the hypotenuse is 0.707. The ratio of this to the total circuit impedance is 0.707. So either way, whether you have this positioning for a high pass or you flip it for a low pass, it's this ratio from here, this out of this, or this side length to this hypotenuse. The ratio is going to be 0.707. And that's why the formula doesn't change and so on. When you are looking at this at the bench, you will simply put an input signal, a sine wave, here. Put a sine wave input, watch the output, and if you were doing the low pass, which was the first example, you would just maybe make this 1 volt. That makes life easy. And then increase the frequency until this becomes 0.707 volts. And that could be, peak or peak to peak, whatever. You would just take a low frequency for the low pass, start low, get it set so that you have a 1 volt peak, and then increase the frequency until the output drops to 0.707 on your scope. And then for this example, now we have the high pass. It'd be the same thing, but you would start high. You would put 1 volt peak at a high frequency so that you have essentially the 1 volt peak output. Then as you decrease the frequency, your output would drop to 0.707, and that would be for your high pass test. You will also see on your scope screen that as you change the frequency, there will be a phase angle change that occurs between the input and the output. And in fact, another indicator that you've got to the cutoff frequency, you'll see, I think we'll see 45 degrees between the input and the output. We might have to double check that, but it's going to make sense. We have to think about what we're looking at. Don't worry about that. I just kind of mentioned that parenthetically. The phase angle. I don't want this intro to filters to get too lost in the details. I mean, they're there of all this stuff, but we can have that to play with and experiment with. But the most important thing is the more broader concepts of voltage division and watching. But I guess I wanted to mention the phase angle because it will be present, and I don't want you to think there's something wrong with that. Yes, there'll be phase shift from the input to the output for this type of very simple, basic filter.